Hello guys, you're viewing Mathematical Build channel, and today I'm going to explain you the basics of arithmetic functions in order of an element. So let me introduce to our channel. So it's Mathematical Bridge. The code, code is road to maths. Goal is road to maths, and I'm going to explain you arithmetic functions in order of an element. That's our logo. So do subscribe to our channel and share the video. So we are student base, and we have started a campaign based on PRMO and Olympiad mathematics, and further we are planning to give out more lectures of more branches of mathematics. So anyway, let's start a lecture. So before I start, first let me explain you what are arithmetic functions. So arithmetic functions are very important functions which are sometimes used to write in number theory. And for example, the Riemann hypothesis, which is a very famous conjecture on which the whole number theory, the modern theory, number theory, which is going to be yet established further, is based on Riemann hypothesis, and which is made up of zeta function. And arithmetic functions have also application in number theory, combinatorics, counting probability analysis, analytical number theory also. Now, what is zeta function? So zeta function is means that zeta of s is equal to sigma 1 upon n raised to s. Yeah, I know you're confused by these symbols. So let me explain. Zeta of s is basically, so s can be any number, and n starts from 1 to 3. So if s, let's say, is 1, so we will have 1 plus 1 by 2 plus 1 by 3. It goes on and on and on and on, dot 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 dot, dot. 1 upon any number you like. Infinity, very large number. It goes and on and on. And the amazing part is that this is infinite. So it means that it does not converge at any value. So for example, we have, let's say, 1 plus 1 by 2 plus 1 by 4. So you know it's a GP, and you can evaluate it and tell me that it is tending towards 2. Means it is approaching to 2, and it cannot be greater than 2. But that's not true for this expression, 1 plus 1 by 2, 1 by 3. It goes on to infinity. And the amazing part is that for every s greater than 1, and vice versa. So if s is greater than 1, then zeta s converges, and if s is less than 1, then if s is less than equal to 1, then zeta s diverges. So it goes on to infinity. And for zeta 2, which is means that 1 upon 1 square. So 1 upon 1 square plus 1 upon 3 square, so on till infinity square. So very large number is tending towards a value that is very surprising, which is pi square by 6. The proof of there is out in YouTube. You can watch You can search this videos out there. It's very surprising, and it was proved by Euler. So anyway, let's move on. So Mobius function is defined as mu of n is equal to 1 if n is equal to 1, and minus 1 raised to m if n is square free. Square free basically means that it is not a square of a number. It's not square free. So it means if n is a square, then we will have it to be 0. Mu of n to be 0. So mu of 4 is 0. And minus 1 is to m. So if we have mu of 6 equal to 2 for m, mu of 6 is equal to minus 1 raised to 2. And why it is minus 1 raised to m? Because there is a conjecture out there which states that the number of even number of devices have probably the number of numbers having even number of devices, even number of primes in its devices is equal to number of numbers having the odd number of primes in its devices. And that's a conjecture out there which is very important to prove the Riemann hypothesis. And I forgot the name of the conjecture, and so do comment down it. So now let's move on to the Dirichlet delta function. So it's very simple, and I know you may be curious that why are so functions defined and why this simple functions are defined. So these functions have a purpose, like I had told you about Mobius function. It had the purpose of solving a conjecture. So it's already defined. So to avoid those steps, now sigma delta of n is equal to 1 if n is equal to 1, 0 if n greater than 1 is used in analytical number theory. So I won't be talking about its application. So modulus function is what should I say? Takes away all the negativity. So basically, if you have a negative number, let's say 3.148, whatever. So we have pi here. So it will return the positive value. So it will remove the negative sign and you will get pi. And mod of pi is also pi. So it's very simple. So yeah, mod of a is mod of minus a. You can see that mod of minus pi is equal to mod of pi. Mod of a by b is equal to mod of a divided by mod of b. Yes, and these are properties which you can verify and check. Now let's move on to the most beautiful part of number theory, which is called GIF and FPA. So GIF is basically we define number theories. We don't want decimals, we hate decimals. That's why we want integers. That's why we define this function which is called GIF of x. So what it does is, so x is any real number, it takes out the fraction part of decimal part, whatever you want to tell it, and gives out the integer. The GIF of x is an integer. And the fraction part of x, the decimal. So these are some important identities. So fraction part is always has to be less than 1. And you can also see that x, the number has to be always greater than GIF of x. And GIF of x is a number less than the real number. So pi is 3.14. So GIF of pi is equal to 3. And GIF pi is less than GIF of pi plus 1. So 3.14 is less than 4. So that's an example. And GIF of x plus m is equal to GIF of x plus m. You can verify it also. Or so GIF of x plus 1 is GIF of x plus 1, and then you can do it by induction. GIF of x plus 1 is equal to GIF of x plus 1 is very obvious to see. And GIF of x plus GIF of minus x is equal to 0. So yeah, for minus numbers, so negative numbers, for example minus 2.1, the GIF of it would be minus 3. And this is because the fractional part always has to be positive. So fractional part function, this is a famous, this is an important identity you should remember, that is x is equal to GIF of x plus fraction part of x. These are some properties. This one I have told you. Now ceiling function. Ceiling function is basically the opposite of GIF function. So it gives a number greater than the value, number greater than the real number given, integer greater than the real. So 3.14 pi, you will have 4 of its ceiling function. So ceiling function is basically the, we are calculating the number above, like the ceiling which you have in homes, so it's above. These are the basic things. So now let's do some questions. So we have GIF of n by 1 plus GIF of n by 2 dot 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 GIF of n by n plus GIF of 2 n is even. Now before you evaluate this expression, let's put some values of n and check what we are getting. So if you put n is equal to 1, we are getting, so let's define this this expression to be fn. So we will get fn equal to 2. Now let's put n is equal to 2. Then we'll get fn equal to, so 2 by 1, so 2, 2 plus 3, 3 plus root of 2 is 1.4, so 4. Now let's put n is equal to 3. So fn would be 3, 4, 5, 6. Now let's put n is equal to 4. So 4 by 1 plus 4, 2, 6, 7, 8 to 10. So f of n equal to 10. Actually, let's just calculate, remove this root of n. So 1, 3, 5, 8. Now I can see a pattern right here that this expression is basically the sum of divisors of 1 plus sum of divisors of 2 plus sum of divisors dot 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 plus sum of divisors of n. And how did I got it? This basically I did this. I calculate the difference of these numbers. Fn 1 and 3 I got 2. And here I also got 2. And here I got unexpectedly 3. And I noticed that the number of divisors of 4 is 3. Number of divisors of 2 is 2. And now what is left is to generalize this. Now let's generalize it. And we are going to do it by induction. So P of 1 is true. P of 1 is equal to S of 1, which is true. So P of n is defined, this expression is defined as P of n. And P of n is basically 1 and sum of divisors and number of divisors of 1 is 1. So P of 1 is true. So now we'll do the inductive step. So Pn is equal to this expression. And now what we have to prove is basically that P of n plus 1 minus P of n is Sn. So then our statement would be true. So let's evaluate P of n plus 1. P of n plus 1 by 1 plus n plus 1 by 2 up till GIF of n plus 1 by n plus 1. Now, if you notice that if n, let's say, is a divisor, we have a divisor, okay. So if you notice that there is not much difference between n and n plus 1, and so the GIF would not much change. So let's find some. So for example, let's take this GIF of n plus 1 by 2, and let's say if n is divisible by 2. So if n is divisible by 2, then GIF of n by 2 is equal to GIF of n plus 1 by 2. And similarly, let's check it for GIF of n plus 1 by 2. Now, if you notice that if n is divisible by 3, then GIF of n by 3 is equal to GIF of n plus 1 by 3. And if n is congruent to 1 mod 3, then also it is equal to, these both are equal, GIF of n by 3 and GIF of n plus 1 by 3. Now, if you take n is equivalent to 2 mod 3, then you will get GIF of n plus 1 by 3 minus GIF of n by 3 equal to 2. So you'll notice that whenever the number of divisors, the n plus 1 by r. So if r is a divisor, then GIF of n plus 1 by r minus GIF of n by r is becoming 1. And so p of n plus 1 minus p of n is equal to number of divisors of 2. This was a simple observation which we had to do. So divisors of n we can denote it by dn, and by induction we can prove. So this means that p of n plus 1 minus p of n is b. Now so let's write down what we have got till now. So p of n plus 1 minus p of n equal to, we have got number of divisors of n. And you notice that why should we not take this whole expression to be f of g of n, let's say g of n, and do the inductive step, because p of n plus 1 minus p of n is d of n, and d of n is mostly, so if n is not a perfect square, then d of n would be even. So most of the time it is even. So let's say if the n is not a perfect square, then we will have p of n plus 1 minus p of n to be even, and GIF of root of n, we need to evaluate GIF of root of n plus 1 minus root of n, GIF of root of n. And if n is not a perfect square, then actually this should be d of n plus 1. Slight mistake here. D of n, so d of n plus 1. So if n plus 1 is not a perfect square, then so if n is not a perfect square, then we will have n plus 1 equal to k square plus 1, k square plus 2, and so on. K square plus 2k. So this means that n will be k square dot 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 k square plus 2k minus 1. So this means that GIF of root of n plus 1 would be GIF of equal to GIF of root of n. So this means this would be 0 and this would be even. So this means that g of n plus 1 minus g of n would be even. So if n plus 1 is not a perfect square, then it is true. Now let's check for when n is plus 1 is not is a perfect square. So if n plus 1 is not a perfect square, Sorry, if n plus 1 is a perfect square, then we will have number of divisors to be odd. So d of n would be odd, so this would be odd. And we need to evaluate GIF of root of n plus 1 minus GIF of root of n. Now what we are going to do is, we are going to do some algebra here. We are going to substitute GIF of root of n plus 1 to be k. So this means that n is equal to k square minus 1. So this means that GIF of root of n is equal to k minus 1. So this means that the difference would be equal to 1. So odd plus 1 is equal. So in both the cases it is even. So this means that p of n plus 1 minus p of n is equal to 1. G of n plus 1 minus g of n equal to 1. And g of 1 you can calculate, it is equal to 2. So it is even. Thus reductions well placed. And therefore we have solved an RMO problem. And yeah, that's an RMO QIQ. Now let's look at another problem from different PF. So this is a very amazing problem. So it uses the most basic identities and induction. So first what we are going to do is use the identity bracket FPF of x is less than equal to 1. So you will have LHS less than, actually less than GIF of x. So what we are going to do is we are going to take GIF of x to be t because it's an integer, and we like to replace integers variables. And notice that RHS, so LH is equal to RHS, and RHS is greater than t raised to t minus 1. Now what you'll notice that this is an exponent and this is a polynomial. But we know that exponent is always greater than polynomial. This means that for some t greater than or some, so this means that there is a bound for n. What we are going to prove is that, so if you substitute some values, t is equal to 1 is true, you can see that t is equal to 2 is also true. No, it's not true. Wait a minute. Yeah, it's true. But now for t is equal to 3, you will check, you will get here 9, 3 square, 9, and you will here get 7. That's contradiction. So what we are going to, so what this gives us an intuition to prove that t raised to t minus 1 is greater than t factorial, greater than or equal to t factorial plus 1 for t greater than equal to 3. And now what we are going to do is here, we'll take t common here, we'll take the variables on one side. T raised to t minus 2 greater than, so we need to prove t raised to t minus 2 greater than t minus 1 factorial for t greater than equal to 3. So for t greater than equal to 3, it also means t greater than 2. Dot dot dot, it means t greater than 3, t greater than t minus 1. So now you notice that there are t minus 2 inequalities here from 2 to t minus 1. So t raised to 2 t minus 2, and 2 is basically 1 into 2. So we have t raised to t minus 2 greater than t minus 1 factorial. Thus we have proved what we needed. So 40 greater than equal to 3, this holds true. So this means that does not hold true, and we have a contradiction for t greater than equal to 3. So this means that t is equal to 2 or 1. So now let's put t equal to 1. So if we'll put t equal to 1, GIF of x is 1, so x raised to 0 is 1. 1 minus 1, 0. So bracket of x is equal to 0. That means that x is equal to 1 plus 0, so x is equal to 1. And that's the only solution for t equal to 1. Now if you'll put t equal to 2, then you will have x equal to 2 plus bracket of x. And this is true because GIF of x is equal to 2, t is equal to 2, and this the basically the outcome of it. So this means that x, so any real number greater than equal to 2 and less than 3 is also satisfies this condition. Now let's move on to what we say the order of an element. So what this basically tells us that, let's take any positive integer a is 2, and a is congruent to some remainder mod m, and let's take another number m. And let's square it first, then cube it, then raise to 4 it, so on. And then we'll find this least positive integer n for which it is congruent to 1 mod n. Leaves the remainder on division by m. So n is the least positive integer, and all this n to be the order ma. So n is order m. So m is the divisor, and a is the number. So this is the order. N is the order which divides phi of m. So a is to phi of m is congruent to 1 mod n. We know that by Euler's theorem. Now let's do some question on that. So we have to prove that order of 2 modulo 100 is 100. So we have to prove that 100 is the least positive integer. You know that 2 raised to 100 is congruent to 1 mod 101. So if you prove somehow that 2 raised to 50 is congruent to minus 1 mod 100, and this also means that order is divisible by this. So if we prove that 2 raised to 50 is congruent to minus 1 mod 101, that would mean that any divisor of 50, let's say it is congruent to 1 mod 101. So t is to 50 divided by, so d is congruent to 1 mod 100. So it's a divisor. So we'll multiply raised to x raised to 50 by d. We will have 2 raised to 50 congruent to 1 mod 101, which is a contradiction. Or it would mean that 1 is congruent to minus 1 mod 101, which is not true. It would mean that 101 divides 2. So this means that if we prove 2 raised to 50 is congruent to minus 1 mod 101, then it would mean that 2 raised to 100 is the least order of it. That's a very good thought, because you can't waste your time calculating for every divisor that it's not the order and it's not congruent to 1 mod 100. So now let's do that. So 2 2 raised to 7, 2 raised to 10. Let's take 2 raised to 10 is congruent to 1024, which is congruent to 24 mod 100. Now let's square it. 576, so it is 76. Now let's again square it. 2 raised to 40. 76 square. 70 plus 6 square basically. 4900 plus 36 plus 4900 or 0 more 100, so leave it. 36 plus 140, 48, 40, which is 40, is 76 mod 100. Now 76 into 24 basically will get 2 raised to 50, remainder. 76 into 24, so minus 576. And minus 576 is 24, and I've done some mistake. So I think 576, 76 more 100, 2 raised to 40, 76 square. I think I've gone wrong somewhere. 36, 140, 40, 76, 2 raised to 40 is congruent to 76 mod 100. 76 into 24. Oh, sorry, we were working in mod 101. 2 raised to 10 is congruent to 101 into 10, so 14. 14 mod 101. Now we'll raise to 5. Let's do some basics. So 2 raised to 20 is congruent to minus 6 mod 100 and then 1. Now we'll again square it. 2 raised to 40 is 36. So 36 mod 101. 2 raised to 10 is 14. So 36 into 14. Now we'll evaluate mod 100. 36, 684 into 6. And 4, 504, which is congruent to minus 1 mod 100, 505, which is divisible by. And thus, as 2 raised to 50 is congruent to minus 1 mod 100 is the least modular. And there is also a theorem which states that for order of p, which is order of any number p with respect to p, so order of p a is equal to p minus 1. There's a specific condition for p also. So anyway, now let's solve another problem. A very good problem. So f, we need to evaluate f of 84. First, let's see the problem. It says n greater than 1000, then fn is equal to n minus 3. For f of n less than 1000, we have f of n plus 5. So we need to evaluate f of 85. So before we directly put the value, let's play with it. So you'll see that f of n is equal to f of n plus 5. And f of n plus 5, put it n plus 5. So plus 5 would be. So basically a number plus 5. So n plus 5, we'll have number plus 5. So f of n plus 10. F of n plus 5, f of n plus 10. And now you can replace f of n plus 5 here with this. So you will have a new value of f of n in terms of f of n plus 10, which would be f of 3 times f n plus 10. What I'm going to define is that the number of times f is appearing, I'm going to raise to it. So by this pattern, there were 3 times 5. So we had in the last term, we had n plus 5 into 3 minus 1. So for f raised to 185, we will have f of 84 is equal to f raised to 184 brackets. So 185, sorry. So we will have 84 plus 5 into 85, 185 minus 1. 84 plus 5 into 184. So 1004 we will have. And for fn greater than equal to 1000, we have this. So we will have basically f raised to 184 1001. And now f raised to 183 1001 again. So we will have f of 990. Now we will again have 998. So we'll subtract, not subtract, we'll remove one function we'll replace f of 998 by 2 times f and n plus 5. So f of 1003. So we will have 180 f of 184 1003. And now we will have f of 183 182 997. And now 997, so we'll again add 5 here. F of 183 raised to 93 1002. Now again we'll subtract 3. So we have 182 999. Finally we will have again 1004 f of 183 107. So you will see the pattern that we can define this loop to be from f of n 0 raised to f raised to n 1004, we get f raised to n minus 2 1004. So this pattern will continue and we will have f3 of 1004. And now let's evaluate this. So f of 1004 is basically, so we'll have f square 1001 f of 998, and f of 998 is basically f square 1003, and now basically f of 1000, and f of 1000 is basically 997. So this was a very interesting question. We played around functions. So f of 84 is 997. Similarly, you can calculate f of 27 and comment down your answer. And digital sum is basically the digit sum of digits. So number of divisors function, we'll move on to number of divisors function. So if you have attended my classes, so you know that we do a prime factorization and we calculate it. Pn raised to alpha n, so number, so tau of n, so prime factorization of n is this, would be equal to alpha 1 plus 1 go on till alpha n plus 1. That's basically the sum of divisors function, number of divisors function. And sigma m is sum of divisors function. You not taught this. And when sigma of m is equal to 2m, then it's perfect number. So perfect number example is 6. So 1 plus 2 plus 3 plus 6 is 12, which is 2 times 6. And it has various applications, and mystery behind perfect numbers, that are there infinite perfect numbers? And the answer to this also surprisingly lies. So anyway, how to calculate sum of divisors? So you have a number m equal to p1 raised to alpha 1 dot pn raised to alpha. You need to calculate the sum of divisors. What you will do is 1 plus p1 square. Let's calculate first the divisors of p1 raised to alpha. Now we'll calculate. So if you notice that p2 plus p1 p2 is also divisor, and all the way p2 p1 raised to alpha 1 is also divisor. Similarly, p2 plus p2 square is also itself a divisor. So p2, so I'm sum of divisors we are doing basically. Up till p2 raised to alpha 2 is also a divisor. And so we'll notice that if you take common p2 here, this will take common, then you will have 1 plus, so I hope you got the pattern here, that they are multiplying p2 here in this term, p2 square, and that is also part of the divisor only. So 1 plus p1 plus p1 square up till p1 is to alpha 1 multiplied by 1 plus p2 go until p2 raised to alpha 2. Similarly, now you have noticed that this is a multiplicative function. So all this will be multiplied in a similar way, and you all know GP, so you can write this expression properly like this. P1 is to alpha 1 plus 1 minus 1 divided by P1 minus 1 and so on, right? So now if you have understood, then please do comment down the number of divisors of 28 of 6023 00. Thank you for watching the video. If you like the video, please do comment down which is your favorite number theoretic function from which I've taught. So thank you for watching.